Hi everyone. In this presentation we introduce the reader to hexadecimal numbers, hexadecimal representation and binary representation. Usually we write numbers in base 10. So if for example I use the number 893,452, so this refers to the following operation. So 8 times 10 to the power 5, 9 times 10 to the power 4, 3 times 10 to the power 3, and so on. Okay, so the rightmost number multiplies 10 to the power 0. The second leftmost number multiply 10 to the power 1, and so on. So we read numbers from left to right, actually. Okay, so to know the value of a number, we need to know exactly what is the rightmost character. There's nothing I can do with the first 8 if I don't know that it's at position 6 here. And we begin with 10 to the power 0, so we start counting with 0. So 0, 1, 2, 3, 4, 5. So if there are 6 characters in the number, so the first number multiplies 10 to the power 5. Okay, so here we have the operation. So the base 10 representation uses 10 characters. So the characters 0, 1, 2 up to 9. And in base 10, the highest character value is 9. Base 2. So in base 2, we have characters 1 and 0 only. So the number 1, 1, 0, 0, 1, 0 refers to the following operation. So again, we have 6 characters. So the first number, 1, multiplies 2 to the power 5. The second multiplies 2 to the power 4. So the basis is 2, and the rank gives us the power. And we read the number from right to left. The base 2 representation uses 2 characters, 0 and 1. And in base 2, the highest character value is 1. How do we convert a number like, for example, 76 from base 10 to base 2? One method that we can use is the successive division by 2. So if I divide 76 by 2, I get 38. So 76 is 38 times 2 plus 0. There's nothing left. Okay, but 38 is much bigger than 1. So I need to divide 38 by 2 again. That gives me 19. So 38 is 19 times 2 plus nothing left. Okay, but 19, I cannot use 19 in base 2 representation, so I need to divide 19 by 2 again. So 19 divided by 2 is 9.5. So 19 is 9 times 2 plus 1. But 9 is greater than so whenever the number I obtain that multiplies 2 is bigger than 1, I need is equal to 1. Whenever the result here is bigger than 1, I need to divide again by 2, okay, so that I can close the number. And we do this until we obtain 0 times 2 plus 1, okay, and from then on we'll be dividing 0 by 2 forever, okay, which will give us 0 times 2 plus 0. So the actual base 2 representation of 76 here is the last column of all these operations. So the first number we obtained is 0. That's 0 times 2 to the power 0. The second residue we obtain multiplies 2 to the power 1. The third residue we obtained, which is 1, multiplies 2 to the power 2, and so on. So if I take the rightmost column here and I let it fall on my right, so that gives me my base 2 representation of 76. So the base 2 representation of 76 is 0, 1, 0, 0, 1, 1, 0, 0. In base 16, we use 16 as the basis. So 8, 9, 6, 4 in base 16 refers to the following operation. So 8 times 16 to the power 3 plus 9 times 16 to the power 2, and so on. In base 16, we need 6 characters to represent the values 10, 11, 12, 13, 14, and 15. And these characters are the letters A, B, C, D, E, and F. So the base 16 representation uses 16 characters. So for example, the number 45A 8F in base 16 refers to the following operation. So whenever we see A, that's 10 times 16 to the power of the rank. F, 15 times 16 to the power corresponding to the rank of the letter F. How do we convert like a number in base 10 to base 16? So we do the same thing. So we divide successively by 16 until we have no more residue. Okay, so here if we do it with this number here, so we obtain 12 times 16 to the power 0, 2 times 16 to the power 1, 6 times 16 squared, and 15 times 16 to the power 3. So if we replace 12 by C and 15 by F, so that gives us F62C. So 63,020 in base 10 is written F62C in base 16. Good. How do we convert a number in base 2 to base 16? So what is that number? So this number here is 0. So we have a 32 character binary number, which means that the leftmost character multiplies 2 to the power 31, and the rightmost character multiplies 2 to the power 0. So here the first four numbers multiply 2 to the power 31, the power 30, 29, 28. The second four characters 2 to the power 27, 26, 25, 24. The following four characters 2 to the power 23, 22, 21, 20, and so on. Each time, so we have at least, so I can isolate 2 to the power whatever, so that within the parentheses I always have a number that multiplies 2 to the power 3, 2 to the power 2, 1, 0. So here 2 to the power 3 times 2 to the power 28. 3 plus 28 gives 31. And here 3 plus 24 gives 27. So here I just isolate whatever I need to isolate, so that here inside the operation here my maximum exponent is 3. And here 2 to the power 28, so here these are all multiples of 4. Okay, because I grouped all the numbers 4 by 4, so 28 minus 4, 24 minus 4, 20, 16, 12, 8, 4, 0, all multiples of 4. So let's isolate 2 to the power 4. Well, in fact, 2 to the power 4 is 16. So here's my number. So we have here 4 times 16 to the power 7, 0 times 16 to the power 6, 12 times 16 to the power 5. So here what I do, how do I obtain 12? So 1 to the power 3 is 8, plus 1 to the power times 2 to the power 2. So this is 4. 8 plus 4 is equal to 12. Okay, so 12 times 16 to the power 5. So the hexadecimal representation of the binary number that is written here is given by is 40C0B954. So we went the hard way here. We could have used a much shorter route. Okay, so if I want to convert a base 2 number into its hexadecimal representation, so starting from the right, I group all the characters 4 by 4, and I extract the hexadecimal representation of this 4-character binary number. So 0 times 2 to the power 3 plus 1 times 2 to the power 2 plus 0 times 2 to the power 1 plus 0 times 2 to the power 0 is equal to 4. Okay, and this is 5, this is 9, this is B. So 4 ones would be equal to 15. So that would be F. Okay. More generally, if you use this table here, 4 zeros in base 2 is equal to 0 in base 16. And 0, 1, 1, 1, 1 in base 2 is equal to 7 in base 16. So here we hit the letters once we reach the binary number 1, 0, 1, 0, which is equal to 10 in base 10, so A in base 16, and so on. So each time whenever we group a 4-digit binary number, we can always extract one of the hexadecimal character.